Okay, can you see my screen?
Yes.
Okay, great. So, hello everyone. This section is about automatic machine learning for recommendation system. So recently, deep recommendation systems have attracted a lot of attention from both the industry and the research communities. So they mainly two advantages. First, they have strong ability to represent the features of users and items. And the second, they are good at modeling the nonlinear relationship between users and items. So typically, a deep recommender system contains three parts: the embedding layer, the interaction layer, and the inference layer. So the embedding layer transforms users and item features into the low-dimensional embedding vectors, and then we capture the relationship between any two features by the interaction layer. And finally, they are passed through the inference layer to calculate the prediction results. So, however, most existing deep recommender systems are based on the manually designed architectures, but this requires a lot of extra knowledge of deep learning and the recommender system, and it also takes a lot of time and engineering effort, and sometimes human mistake and bias could lead to suboptimal architectures. So why we believe AutoML can somehow address these challenges. So AutoML allow you to provide the labeled training data, the metric you want to optimize, and some constraint as input, and you will directly receive an optimized model as the output. So if we introduce AutoML for deep recommender system, the architecture are designed by the machine automatically. So this requires less expert knowledge and save a lot of time and human effort. And if we input different data, the output model is different. For example, the news recommendations and the video recommendations, because we use different data, we have different features. So we will have different models. So in general, there are two groups of AutoML methods for neural network architecture search. So one is RL-based method. So the high level idea is to introduce a controller network, which learn to select the optimal component from a large candidate set. For example, in this case, we define some candidate components such as convolution and pooling, and the RL-based AutoML has two parts. One is the controller, which learn to find more processing component, and the other part is the child architecture, which is a deep neural network with the selected component. And the components of the child architecture are sampled by the controller, so the child architecture may be different each time. So the process of RL-based AutoML is that given the candidate component, like C1 to C3 in this figure, so we will sample a component by the controller, and then we get a model with this selected component, and then update our model parameters by minimize the training loss. And next, we evaluate the model on the validation set, and we use the model performance as the reward to update the controller. So this is the training process of RL-based AutoML methods. So the second group of AutoML methods are gradient descent-based methods. So the algorithm is based on the continuous relation and the gradient descent in the architecture space. So for example, in this figure, given the three candidate components, we will weighted sum the output of three candidate components according to the controller weight, and then we get a model. And then we update the model parameters by minimize the training loss, which is the same with the RL-based method. But the difference is we update the controller parameters by minimizing the validation loss. So these are the two well-known AutoML methods. So in this section, we will introduce three sets of applications of AutoML in deep recommender systems. One is AutoML for embedding layers, and the second is for the interaction layer, and the third is AutoML for loss functions. So we will first introduce the embedding layers. So in the real-world recommender system, they usually contains hundreds of feature fields. This feature field comes from the users, items, contextual informations, and their interactions. So as we mentioned before, deep recommender system will transform features into embedding vectors. For in most existing systems, they assign the same embedding dimension to all the features. But I think this way use the embedding memory inefficiently because I think there are three reasons. So one is actually an embedding dimension often decides its ability to capture informations. So if we simply assign the same dimension to all the feature fields, we may lose the information of the important features, but waste memory on the unimportant ones. For example, the location feature is very important in the location-based recommender system. So we should assign it with a large dimension. So this is the first reason. So another reason is actually different feature fields have different number of unique values. For example, the gender feature only has two, male and female, but the user ID feature contains millions of unique values. So basically, we should assign larger dimension to the field with more values. Then we can encode more information of them and capture their relationship with other features. And finally, different features have different frequencies. For example, in the game recommendations, feature male appear much frequently than the feature female. So we should assign larger dimension to the feature male. So according to these three reasons, we should assign different dimension to different features. Next, I will introduce four papers of AutoML in embedding layers. So this first paper is introduce a multi-set embedding. So the intuition is that we don't need to have a large dimension size for all the items. We only need to have a large dimension size for the head items. This is because the items appear very frequently in the training data set. So it means that there will be more information to be captured. So we need to have a large dimension for these head items. But on the other hand, for the tail items, because they appear less frequently in the training set, which means they have less information to be learned, so we don't need to use a very large embedding size. So then the multi-set embedding settings are introduced for the embedding matrix. So in this example, we have three features, and where each feature has the largest largest allowed embedding matrix size, 10 million by 256. So we first need to sort the items by their frequency, and then we can cut the embedding matrix into small pieces. So here we cut each matrix into 5 chunks horizontally and 4 chunks vertically. So the way to cut the embedding matrix could be predefined. So here the paper used reinforcement learning based AutoML approach, and they have a main model that contain the largest allowed embedding sets for each features. And then in each interaction, the controller samples embedding sizes and receive a reward from the main model. So over the training process, the controller will sample many different types of embedding sizes, and eventually the controller will convert to the size that generates the highest reward. So here the reward is defined as the quality reward RQ minus lambda, which is hyperparameters, and multiplied by a memory cost CM. So the quality reward is a metric to optimize the main model, such as the AUC for the ranking problems. And the memory cost is a measure of overall budget memory usage of the controller's choice. And given this reward definition, the controller is trained using the A3C algorithm. So this is the first paper. However, one challenge of this model is it assumes the items frequency are pre-known and they are fixed. But actually in the real recommender system, the items frequency are not pre-known and they are highly dynamic. So we propose our model ESAPN. So this is an overview of the framework. And in this framework, we investigate the recommendation task in a screaming setting. And the framework contains two parts, the recommendation model and the policy model. The recommendation model takes users and the item pairs as input to predict the user preference for the items. And the policy network serves as an RL agent to adaptively adjust the embedding size of the users and the items. So given the user item pair in the data stream, the policy network first selects the appropriate embedding size for both users and the items. And next, we look at the embedding table to obtain the embeddings of the users and the items with the selected size. And then the embeddings are fed into the recommendation model to calculate the prediction result. And the recommendation model is updated according to the ground truth label. And the predictions are passed through a reward function to compute a reward. And the reward is finally used as a signal to update the policy network. So we first detail the deep recommendation model. So suppose we have n candidate embedding sets of users and items from D1 to Dn, and given a user and the item with the selected embedding sets, we get their embedding vector from the embedding table. So since in the input dimension of the following inference layer is fixed, so we need to unify the size of the input embeddings. So we introduce a series of linear transformation to map the embeddings to the next dimension. For example, we map the embedding E1 with dimension D1 to the embedding E2 with dimension D2 by the first linear transformations. And in this way, for each embedding, we map them into the largest dimension Dn by the cascading linear transformations. And next, we concatenate the transformed embeddings of users and items and feed them into the inference layer. The inference layer is implemented by the multi-layer perceptions with M hidden layers. So the policy network serve as the RL agent that are dynamically adjust the size of users and items. So here the environment is the deep recommendation model, and the state contains two parts, F and E. F is the frequency of the users or the items, and the E is the current embedding size of users or items. So then, based on the frequency and the current embedding size of users and the item, the policy network chooses two possible actions to adjust the embedding size. One is enlarge, and the other is unchanged. So enlarge means to enlarge the embedding size to the next larger candidate embedding size, such as from D1 to D2. And the unchanged indicates to keep the current embedding size. So here, the policy network is also implemented by the MLP, and the reward is defined in the following way. So given a user item pair, the recommendation model makes predictions and return a loss based on the ground truth label. And we use two queues, first in, first out queues, LU and LI, to maintain the latest T predictions, T prediction loss for the user U and the item I. And given current prediction loss of the user U and the item I, the reward are calculated as the difference between the average of the latest prediction losses and the current loss. So this is the model part of this paper. So in this figure, we show the average performance of the items or users with frequency from 1 to 100. And the red curve is our model. So we can observe that our model has best performance for any frequency during the training. So this is the second paper. The third paper is a field-aware embedding dimension search in recommender system. It aims to assign different embedding sites to different feature fields, such as age or gender. So this is also a challenging task. I think the first challenge is the relationship among embedding dimensions, feature distributions, and the neural network architectures is very complex. So in other words, they are highly dependent on each other. If we change one, the others will also change. So this makes it harder to manually adjust the embedding dimension separately. So this is about the first challenge. So another challenge is actually the real-world recommender system often contains hundreds of feature fields. So if assign k candidate dimension to each field, then the total search space is m power of k. So this is a very large search space. So manually selecting from all combinations is very expensive in both time and the computations. So to address these two challenges, we propose an AutoML model, AutoDeep. So our model can automatically select the embedding dimension to different feature fields. So this is the overview of our framework, and we have two stages. So in the dimension search stage, we first assign a set of candidate dimensions to each feature field, and these candidates have different dimensions. And then we will unify the candidate embeddings to the same dimension. This is because we will fit the embedding into the MLP layers later, and the input dimension of MLP is predefined and fixed. So it cannot handle the various embedding dimensions. That's similar like the last paper we introduced. So we need to first unify the candidate embeddings. And finally, we weighted some of all the transformed embedding and feed them into the MLP layers. So here, the weighted sum probabilities are also trainable, and they measure the contributions of different candidate embeddings. So after the search model converges, we go to the parameter retraining stage. So according to the well-learned weights on the candidate embeddings, we can select the optimal embedding dimension for each field and retrain the model parameters. So this is our model part. From this table, the result, we find that our model achieved the best recommendation performance. And at the same time, it can save about 70 to 80% embedding parameters. So this result proves that the effectiveness of our model, and this framework has been launched in 16 real-world applications in ByteDance. So this is about our work to automatically select the proper dimension for all the feature fields. It can be applied to any deep recommender system with the embedding layer. It can save the embedding parameters, and at the same time, it can improve the recommendation performance. And now we have introduced 3 papers to adjust the embedding size of the categorical features. Next, I will introduce the work for the embedding of numerical features. So this is a paper just published at the KD this year. So consider an recommendation data entrance with the feature field gender, day, heat, and average. So the categorical features like gender are directly mapped to embedding by assigning a unique embedding vector to each feature values. But unfortunately, this strategy cannot be utilized to the numerical because there may be infinite feature values in the numerical feature like the heat. So there are two existing methods to handle the numerical features. One is normalization, where all the numerical features all the numerical features in the same field share a single embedding and use a scalar to multiply with their values, such as we can multiply the values of h with the scalar 1 as their embeddings. So this method has a very obvious disadvantage because it assumes all the feature embeddings in the same field are linear related because they multiply with the same scalar. So so all the feature embeddings in this field are linear related to each other. But actually, in the real world recommendation system, they don't have this kind of pattern. So the second method is discretization, where we partition the range of the feature values into buckets. For example, age 18 to 14 as the teenage and 41 to 65 as the middle age. So this method has three disadvantages. First, the discretization process cannot be optimized together with the main model. And second, similar numeric values may have quite different embeddings, such as age 40 and 41, since they are in the different group. And third, we may assign the same embedding to very different numeric values, such as age 18 and age 40, because they are in the same group. So this paper proposes a framework to address these challenges. And first, they assign a set of embedding meta embeddings for each feature field, such as age. And the number of the embedding vectors is hg for the feature field ng. The ng can be age in this figure. And then, given a specific feature value, such as age 18, we can calculate the probabilities over the embedding vectors in the meta embedding table. This is by a compute by a controller network. And finally, the paper proposed three aggregation functions: the max pooling, top k sum, and the weighted average, to aggregate the embedding vectors from the meta embedding tables. And then we can get the embedding of the feature age 18. So this model has two advantages. One is end-to-end, because the discretization of the numeric features can be optimized jointly with the main model. The second is continuous but different, because the different feature values are assigned with the different embeddings, but the closer feature values have the similar embeddings. So this is the two advantages of their model. Okay, now we have introduced the AutoML model in the embedding layers for recommendations. Next, I will introduce the applications in the interaction layer. So as we introduce the data in recommender system is mostly in a multi-field form, and each field is a type of features such as weekday, gender, city, these kind of things. So here we give an example. It has 4 fields: weekday, gender, city, and the product category. And each field have many options. And for this type of data, explicit feature interaction can significantly improve the performance of models. For example, people like to download the popular apps, then the ID of an app may be the signal. And people often download the apps for food delivery at mealtime. Then the interaction between the app category and the time step may be the signal. So we can find some feature interaction can be easily understand, and that can be designed by the expert. That's the 2 examples above. But most other feature interactions are hidden in the data and difficult to identify, such as the diaper and the bear rule. So we hope to manage them automatically by machine learning algorithms. So actually, factorization models such as FM and DeepFM has been proposed to explore the feature interactions, where the interaction of several embedding from different features is captured by some operations, such as the inner product or the neural networks. So these factorization models have been widely used in many real-world recommender systems. So however, these methods are simply either enumerating all the feature interactions or requiring the human effort to identify the important feature interactions. The former one, enumerating all the feature interactions, it always leads to a large memory and the computation cost to the model, and it's difficult to extend to the higher order interactions, such as the third order or fourth order. And the later one, human identify the important feature interactions. It requires a high labor cost, and it has a risk to missing some important interactions. So there are several papers trying to automatically find the important feature interactions. The first one is the AutoFIS from the KDD 2020. So they proposed two-stage method to automatically select the feature interactions in the factorization machine. In the search stage, they select the important feature interactions, and in the retraining stage, they retrain the model with the selected interactions. So how to search and detect the important feature interactions? So here, they set a gate for each feature interaction to control whether its output will be passed to the next layer. So from a data-driven point of view, whether open or close a gate should depend on the contributions of each feature interactions to the final predictions. So the interaction contributing little should be closed to prevent introducing the actual noise and the actual computations to the model training. So the value of the gate are learned by the gradient descent based AutoML method we just introduced before. So this table summarizes the performance by applying their model to FM and deep FM, and we can observe that the auto fees can remove about 16 to 80% the second order feature interactions, and at the same time, they can achieve the better performance. So this is the first paper. So the second paper, auto group, is published in IJCAI' 2020. So the model mainly contains three parts: the auto grouping, interaction, and the MLP. So this slide shows the auto grouping part, which is the most important stage of this paper. So the purpose of the auto grouping stage is that for each order of interaction, we want to find some useful feature set, and then we only need to model the feature interactions within this feature set. Take an example of the order P, and we have several group of feature sets, and initially each feature is possibly selected into the each feature set. And we have two probability values, selection and non-selection. So if the selection is larger than the non-selection, then this feature is selected into the particular feature set, such as the red line represents the selected. And once the feature set are determined, we compute the piece order interaction of the interactions within each feature set. And this model parameters are also learned by the gradient descent based AutoML method we introduced before. So this is the auto group paper. And the advantage is that each order of interactions, we can find some useful feature set, and we only need to model the feature interactions within each feature set. So the third paper in this section is auto CTR. So this paper first build a good search space. It covers sufficient the handcraft architectures such as the MLP, dot product, and the factorization machine blocks. And then we can build them together to form a deep recommender systems. So an example is shown in this figure. So we group the input dense features and the sparse features into two components. So so the features in each group are selected jointly. And then the blocks can take both the raw input or the output from the other blocks. And the final layer will collect all the isolated features to get the final predictions. So the search space is a two-level search space containing both the block parameters and the connection among them. And this paper proposes an evolutional search algorithm to learn these parameters jointly. So this is the third paper of AutoML in interaction layer. And now we have introduced the AutoML in embedding layer and the interaction layer. Next, I will introduce the AutoML for loss function. So in addition to the neural network architectures, well-designed loss function is also very important to improve the performance in different recommendation tasks, such as in the item rating prediction, it is a regression task, and the click-through rate prediction is a binary classification task. So to optimize the deep recommender system, most existing work are based on a predefined and fixed functions, such as MSE and MAE loss for the regression tasks. And then the deep recommender system are optimized in a back propagation manner, which computes the gradient to minimize the given loss on the training data set. So during this process, the key step is to compute the gradient of the neural networks. But it's often unclear whether the gradient from a given loss functions are optimal. For example, in the regression task, MAE loss is more robust to the outer layer, but its gradient are not continuous, making it hard to and inefficient to find the solution. And the MSE gave a more stable and closed form solution, but it is sensitive to the outer layers. So therefore, if we only use a predefined and fixed loss function, we cannot guarantee the optimal gradient for all the data examples. So some existing work develop a method to fuse the multiple loss functions. They can take advantage of multiple loss functions in weighted sum manners. However, this work has some disadvantages. First, they rely on the exhaustively or the manually search for the loss weight from a large candidate set. So these are extremely costly in the both computation and the time. And also they aim to learn a set of unified and static weight over the loss functions. So they entirely overlook the different convergence behaviors of different data examples. And finally, when we switch among different deep recommendation system frameworks or the different recommendation data set, we always need to retrain the loss weight. So this degrade their generalizability and the transferability. So here is the overview of our auto loss framework. And we have a deep recommender system network, a controller network, and a set of predefined candidate loss functions. And the learning process mainly contains two steps. The first step is forward propagation. So given a mini batch of examples, the main deep recommender system network first generates the prediction y height based on the input feature x. And then we can calculate the losses of candidate loss functions according to the ground truth label y and the prediction y height. And at the same time, the controller network takes y and y height and outputs the probabilities over the loss functions for each data example. And finally, we can calculate the overall loss L according to the products of the losses and the probabilities. So this is the forward propagation step. And then the next step is the backward propagation. So we first fix the parameters of the controller network and update the deep recommendation network parameters upon the training data examples. And then we fix the deep recommendation network and optimize the controller network based on the validation data examples. So this alternative updating approach enhances the generalizability and it prevents our model selecting the probabilities that overfit the training data examples. And the next, I will introduce the experiment. So we compare our model with three groups of baselines, the predefined and fixed loss functions, the fixed weight over the candidate loss functions, and the data example-wise loss weight. And we can observe that our model outperforms all the baseline methods, that our model can select proper loss weight for different data examples, and it updates the controller on the validation set, which enhances its generalizability. So these results validate the effectiveness of our model in selecting the loss functions. And we also studied the transferability of the proposed controller. And we can find that our controller trained with one deep recommendation model can be applied to the other models directly, and our controller learn on one data set can be directly applied to other data set. So this is our recent work, which can automatically select the proper loss function for different data examples, and it has good transferability. So to summarize why we introduce AutoML for recommendations, because AutoML allows you to provide the data, the metric you want to optimize, and some constraints such as time and cost as the input, and you will directly get an optimized model from the machine. And so if we introduce AutoML, we can automatically design the deep recommender system. It requires less expert knowledge and save a lot of time. And if we input different data, we can directly get different models from the output. For the future directions, most current work focuses on the architecture search of the neural networks. But actually, we can incorporate AutoML to more tasks when we build a deep recommender system, such as the loss function search we just introduced. So in the future, I think we can study more such applications, such as the feature engineering, the model selection, optimization, and the evaluations. So that's all for the AutoML for recommendations. Next, Dr. Fan will introduce the adversarial attack for the recommender systems.